Hello, everyone. In the last sessions, we learned a little bit about graphs and mostly terminology. Uh, Graphs are very useful objects. This is an example of a graph, which is, or rather, a picture or an drawing of a graph. They are used mostly for modeling mathematical problems. In this case, so let's say we have a computer network where we have computers or servers in the city, different cities, and between some of these cities, for instance, between Denver and San Francisco, we have a communication link. And between Denver and Chicago, we have a communication link, and we draw those links as arcs or edges that connect these points together. So we put a point for every city that we have a server in, and we connect those cities by a straight line which have a communication link together. And uh, here we can model our network like with this representation. Now, this representation is an instance of a mathematical object called graph. Here is the definition of the mathematical object, which is a graph, from your book. You should be separating always a graph, which is a mathematically defined object, and any picture of it. So here we have a picture of a graph, and now we want to define a graph as a just mathematical object which we can draw or represent in different ways. All right, so a graph G is by definition a, an ordered pair of two sets, V and E. So it consists of two sets, V and E, which our first set we call V and the second set we call E. The set V, it has to be non-empty, and its elements are called vertices or nodes, and they correspond to these points in here. And E is the set of edges, or sometimes called arcs, and the set E corresponds to these connections between different vertices or nodes. Each edge has either one or two vertices associated with it called its endpoints. An edge is said to connect its endpoints. And the easier way actually to define E is to say that E is a set of E1, E2, some number of elements, and so the definition says that each edge is associated with two objects called its endpoint. It simply says that we can write EI to be so let's first also put some name for our vertices. Let's say our vertices are V1, V2, and Vn. Then each edge is just a set of two vertices. So let's say vi1 and vi2. So each, for instance, here this edge contains the vertex, which here is represents Denver and Chicago. This edge here has Chicago and Detroit. So each edge we just represent by the set of two uh, vertices which the edge connects, and those vertices are called the endpoints of the edge. And the edge is set to connect its endpoints. And another terminology here is the incident. It's very often said that an edge is incident to VI, its endpoints. So EI here is incident to VI1 and VI2 and VI1 and VI2. Each of them are also incident on EI. Okay, so just to make a clear connection between this example and the notation here, let me write for this example. So the graph which has is represented by the computer network here has vertex set, these cities, etc. And the set of edges of the graph are just pairs of the links in communication links here, or the edges in this graph, which are sets. We can represent them by, as I said here, by sets of two of vertices. So let's say therefore, for instance, San Francisco and Denver is an edge, and then we have another edge, which is Denver, Chicago, and so on and so forth. Abstractly, the graph is defined like this, and as a pair of two sets, ordered pair of two sets V and E, where objects of E, you can think of them as uh, just pairs of objects of E. And the reason here the definition says it can be associated with one or two vertices is because it can happen that for an edge both of the uh, endpoints are the same. Like for instance, a graph can have a edge which starts and ends at the same point, and this edge is called a loop. Therefore, we can say that a loop is an edge of a graph or the same vertex. And so the graphs are usually, we can just draw them, and you should note that we cannot always draw on the paper without intersection of edges. But anyway, so let's be this graph, and uh, there can be loops here. So this edge is, for instance, E1, E2, So my vertices here are A, B, C, D, E. Oh, sorry, I have two B's, so I should have A, B, C, D. So let's call this one. What's this? G. So my nodes are A, B, C, G, D, and the edges are these are E1 through E4, E5, and this edge here it just starts and ends at the same point, so it's a loop. And E3 has two endpoints, B and C. And if I want to write down the set, which the abstract definition in the abstract definition, like the sets V and E, so the V is just my set of vertices A, B, C, D, G, and E is E1, E2, E3, E4, E5. All right, but it's much actually much better to think of these EI as the pairs as just a pair of vertices. Another special kind. Now it can be in a graph that there are multiple edges which connect the same endpoints. For instance, like this, we can have an SX that connects B and C together. So in that case, the graph is called a multigraph. So let me write it here. A multigraph is a graph in which there are two edges connecting the same endpoints. And for instance, if you have this loop, there can be another loop also. So these are called multi-graphs. But we are mostly interested in a simpler kind of graph which doesn't include these multiple edges. And in many applications, it's much easier to work with uh, what is called a simple graph. So a simple graph is a graph which has no loops, or or should say, and in which no two edges connect the same endpoint. So more briefly, a simple graph is a graph which is not a multi-graph and also has no loops. And the example of it is what we had seen before, like the network example. So because it didn't have, so it doesn't mean much to have multiple links, etc. Another variant of a graph, which sometimes is used, is called a directed graph. sometimes called a digraph. This is a graph in which we associate a direction with every edge. So let me draw an example. So we have some graph. Now we can put some direction on each edge, and then uh, the result is called a directed graph. So I don't write the definition, but it's clear. And a very easy way to formally define the directed graph is by saying that the graph G, which is the set V, is now such that the set E is a set of ordered pairs. Let's, for instance, Vi1. Instead of just set of two elements, we now take ordered pairs, and so therefore E is just some set of uh, ordered pairs. And when we write the two endpoints in the ordered pair, we mean that the edge is directed from the first element to the second element. So if we want to write that set E for the graph here, so let me uh, assign names to these vertices A, B, C, D, E, and then the set E here for this special case would be C, E, D, C, C, A, and B, C. And directed graphs are used in applications where it is important that we go from one direction to another. For example, they could model one-way roads and the like. Graphs are used in very many different branches of science and many other area in industry to model the relationships between objects and then to study those relations. For instance, one place it's used is in social networks where there are graphs of, like for instance, friendship or what a book called acquaintanceship graph. For instance, Facebook has this famous friendship graph, which is a very large graph, uh, uh, like this one here, which people are connected to their friends. And then they study the properties of these graphs. For instance, they want to know uh, if you want to go from any person to any other person, how many vertices you have to traverse. For instance, you can go from Amy to Jan, and then you can go from this path, you can go from this path. And so there are meanings in what is the shortest path between every two people, and a lot of things you can deduce from the properties of the graph that represent the relations between the objects. Let me also discuss a specific class of graphs which are very useful. So there's the notation K n is called the complete graph with n vertices. So the complete means you take n vertices. So let us take n to be 5 and put in all the edges that you can. Actually, I should say simple. All right, now you put every edge. So let us write every edge that is possible. Right, so everyone should be connected, every vertex, sorry, every vertex should be connected to 4 other vertices. So here 1, 2, 3, 4. Here we have 2. Here we have 3. Yeah. Right, so this one should connect to this. Now we also need to connect this vertex here with this vertex. But you see that there is no way to connect these two without making an intersection. And this is actually indeed true that you cannot do that, but that's not important. So this intersection here is not a node. It just shows that we cannot draw our graph without intersection between edges on the plane. So this here, my nodes here are, for instance, I can say 1, 2, 3, 4, 5, and the number of edges of the complete graph is, you take any possible two uh, element set, and therefore is n choose 2, and this is n times n minus 1 divided by 2. There are many examples of modeling different phenomena in your book using graphs in section 10.1, and they're essentially very similar to each other. And we go to section 10.2 and to learn some terminology about the graphs and the objects in it. Here is a definition of what I called before incidence relation, or and also some similar notions. So imagine U and V are vertices of an undirected graph G. They are called adjacent or neighbors if they are endpoints of an edge E. So let me draw an example here. So here is an edge, V and U. And you should note that adjacency relation and incidence relation as it will be defined here also later, it applies to different objects of different types. So here we have adjacent, two vertices are adjacent when they are endpoints of an edge. And in that case, it's also called neighbors. So U and V are neighbors if they are endpoints of an edge. And they are adjacent if they are endpoints of an edge. And E is called to be incident with U and V, and E is also, as before said, to be incident with, also connect U and V, and we also say that V and U are incident with E. So the next term we learn is that of degree of a vertex. So the degree of a vertex in an undirected graph is the number of edges incident with it. And except that a loop contributes twice the degree of a vertex, and it's denoted by degree of V. So degree is one of the important concepts in graph, and so I just draw part of a graph, so this might continue in different areas. So this will go, and so here we have V, and these are edges incident on it, and let's also have a loop. And the degree of V here is 6, because so this is one edge incident, two edge, three edge, four edge, and one loop. So the loop contributes twice to the degree. So essentially, you look very near V and see how many uh, things are connected to V, how many arcs locally are connected to V. So let's see the first theorem of graph theory. So the first theorem of graph theory is a very simple and nice theorem. Let G be undirected graph. So when we don't say it's directed, then it is an undirected graph. If I just say that it's a graph, then we look at the summation over all the vertices. So G is by definition the set of vertices and the set of edges. We look at all the vertices and sum their degrees together. Right, so this notation, if you recall, says that you sum the degree of V for all the vertices of V. Then the theorem asserts that this sum is equal to 2 times M, where M is the number of edges. In other words, M is the cardinality of the set. So the proof is actually very, very simple, and you should perhaps already see that this is true, because each edge in a graph, let me draw here, each edge contributes 2 to the degree. So if you look at this summation here, so you sum over all the degrees, and each single edge is summed to, is counted twice, once for one of the vertices. Correct? So even if we have loops, it's counted twice in degree of V, and E, if it is not a loop, if it is not loop, it's counted in the degrees of its endpoints twice. And if it's a loop, it's counted in the degree of the single endpoint twice. And therefore, each edge contributes 2 to this left-hand side here, and their sum has to be 2 times the number of edges. This theorem is called the handshaking theorem. So supposedly, because the number of handshakes is twice the number of hands. So if you think about it, maybe it makes sense to call it the handshaking theorem or the handshaking lemma. So here is our second interesting theorem, which is a consequences of the previous one, the handshaking theorem, and it's actually quite very interesting theorem. Take an undirected graph then it has an even number of vertices of odd degree. Again, so for any graph, the number of vertices of odd degree is even. So let's prove that. So from the previous theorem, we know that the summation of the degrees of V over all the vertices is 2 times the number of edges, where M is the cardinality of V. Now I break up the summation here into 2 parts. I write it as the sum over V in V, all those vertices with such that degree of V is odd, plus the sum of those V's in V where degree of E is even. This is again equals to M, right? Because see, this is just the summation of all vertices. I broke up the summation into the 2 parts. So I first sum all of the odd vertices, degree odd vertices, and I then sum all the vertices with even degree. But now observe that this summation here is an even number. Why is that? Because the degrees are even, and so sum of even numbers, I mean 3 even numbers, 4 even numbers, if you sum together, the result will be always an even number. And this guy here is also an even number, and therefore the sum of the degrees of vertices with odd degree is the difference of 2 even numbers, and that is again an even number. And because each one of those guys is an odd number, now the total number of them have to be an even number. So we know that's again, so we know now that this summation here has to be even because it is the difference between 2 even terms. So it has to be an even number. But we know that this is a summation of odd terms. And uh, if you add up odd numbers together, uh, if you get one odd number, it is odd. If you add 2 odd numbers, you get even. If you add 3 odd numbers, you get an odd number. If you add 4 odd numbers, you get an even number. And it's very easily you can just write down by the definition of odd numbers are 2k plus 1. You just see that if you have an summation of some odd numbers is even, their number has to be odd. So let me actually write it for you just here. I write it in top. So let's these numbers be di. So let's di be degree of vi and odd. Then the summation, the red summation there is some sigma. So by definition, then we can write this di as 2ki plus 1. Then this is sigma 2ki plus 1 over some terms. And this is then, so let's say these are all over vi degree odd. Then this is 2 sigma ki plus sigma of 1. And this term is even and this term is just the number of VI's without degree. And again, because this term is even and the summation of these two is here, so this guy here also has to be even, which is the number of VI's without degree.